Today we're going to do one of those what if problems. So suppose you get into an elevator and you start from rest and that elevator starts to accelerate upwards at a rate of 2 meters per second every second. How fast would you be moving if the elevator came to a dead stop? And let's assume for right now that you don't hit the ceiling once that happens. So let's just summarize some of the information contained within this problem. You're going to accelerate upward at a rate of 2 meters per second squared. Your velocity vector is going to also be in the upward direction. Yes, gravity is acting upon you now, but there's this external force causing you to accelerate in the upward direction. Now, your initial velocity, right before you start accelerating upward, is going to be 0 meters per second. Now, our question here is, what is your final velocity after 10 seconds? Now, to find the final velocity after 10 seconds, we're going to use the kinematic equation that says the final velocity equals the initial velocity plus the acceleration times time. Now, in this case, our initial velocity is going to be 0. And so our final velocity can be written as the acceleration times time. Now, acceleration is how fast the velocity is changing. Now, in this case, our velocity is going to increase at a rate of 2 meters per second for 10 seconds. Now notice that my units of seconds squared cancels out with this second, and what I am left with is 2 meters per second times 10 seconds, which will work out to be 20 meters per second. So after 10 seconds, this object, so the elevator and the passenger inside, will be traveling at a rate of 20 meters per second. Now suppose the elevator comes to an abrupt stop. So here you are in the elevator, and the elevator comes to an abrupt stop. Now, once the elevator stops accelerating, you're going to want to keep going in the upward direction due to your own inertia. Objects in motion will remain in motion unless an outside force acts upon them. Now, you're going to be moving in the straight upward direction, and there's only going to be one force acting on you once the elevator stops accelerating you, and that's going to be the force of gravity. Now, gravity is going to oppose your upward motion and start to cause you to accelerate in the downward direction, hence slowing you down. So the question is, how far would you travel in the upward direction before you come to rest, or a final velocity of 0 meters per second? Now to summarize some of the information that we've just been given is, your initial velocity is going to be 20 meters per second in the upward direction, which we're also indicating with this velocity vector in the upward direction. The acceleration due to gravity is going to be negative 9.8 meters per second squared. So every second that you're moving in the upward direction, your velocity is going to decrease by 9.8 meters per second. Your final velocity is going to be 0. That's because you're going to be slowing down until you eventually come to a stop. Then you would start to fall back in the downward direction. We don't know the time it takes to move in this upward direction, but we will find it just to see how long it would take. And we don't know how far you travel in the upward direction. So we're going to find the solution to this. Now the kinematic equation that is most useful in this case is going to be our final velocity squared equals our initial velocity squared plus 2 times the acceleration due to gravity times the change in height. Now notice that the final velocity in this case is going to be 0, so we can rewrite this equation as 0 equals v initial squared plus 2 times the acceleration due to gravity times the change in height. Now the next step is to move this initial velocity squared to the other side. So I'm going to subtract it from both sides. And when I do that, I get minus v initial squared. And when I add v initial squared to negative v initial squared, I get a 0. So then I'm left with just this term, 2 times the acceleration due to gravity times the change in height. And now the next step is to divide both sides by 2 times the acceleration due to gravity. Now when I do that, notice that this cancels out with this, and I'm left with the unit of height or displacement, which in this case, my delta y works out to be negative v initial quantity squared divided by 2 times the acceleration due to gravity. Now in this case, I know my initial velocity is 20 meters per second, quantity squared, divided by 2 times the acceleration due to gravity, which in this case is negative 9.8 meters per second squared. And now when I do that in my calculator, what I get is 20.4 meters. So if there was no ceiling above your head, you would continue to travel for about 20.4 meters until eventually you slow down to a stop. Now, as one additional exercise to that, let's just figure out how long it actually takes you to travel that distance. So in this case, v final equals v initial plus acceleration times time. This is one of our kinematic equations. We know that our final velocity is 0, and in this case, this would then work out to be 0 equals v initial plus acceleration times time. And so what I'm going to do next is I'm going to subtract v initial from both sides. That is, I want to take this term and put it onto the other side. In order to do that, I have to subtract it from both sides. And what you should see is that minus v initial equals v initial minus v initial is 0, acceleration times time. And so the next step I'm going to do is I'm going to divide both sides by my acceleration. What I do to one side, I have to do to another side. This cancels out with that, and I get an equation for my time, which says time equals, or the time it takes for me to slow down from 20 meters per second to rest, is going to be my initial velocity, the negative of my initial velocity, divided by the acceleration, in this case the acceleration due to gravity. And when I plug in the information that I've been given, my initial velocity is 20 meters per second. The acceleration due to gravity is negative 9.8 meters per second squared. And when I do this in my calculator, I get about 2.04 seconds. So that's how long it takes to travel that upward distance of 20.4 meters. Now, as you all know, there is a ceiling in an elevator. And let's say that the ceiling is about 2.4 meters from the floor. So imagine here's our elevator. Of course, I'm not the best artist in the world. So here's our elevator. And the height of this elevator is going to be, say, let's say 5 meters, make it nice and simple. Now, if you have an initial velocity in the upward direction of 20 meters per second when the elevator comes to an abrupt stop, you are going to keep moving in the upward direction. Now, once you become airborne, gravity is going to start slowing you down. But the thing is, we just figured out that you're going to move 20 meters in the upward direction, so you are going to hit the ceiling if the elevator were to come to an abrupt stop. So the question now is, how long would it take before you actually hit the ceiling? And to do that, this becomes a slightly more complicated problem. So let's set this problem up. We're going to use the kinematic equation that says that the change in y equals v initial times time plus 1/2 acceleration times time squared. Now notice that in this case, we don't have any terms in here that equals 0. So let's start working with this information. So you know that delta y in this case is going to be 2.5 meters. This is going to equal our initial velocity, which we said was a plus 20 meters per second. And we don't know what the time is. That is, we're looking for how long it takes your feet from the moment it leaves the ground to the time when your head impacts the ceiling. Now, in this case, this is going to be plus 1/2 negative 9.8 meters per second squared. That's the rate at which gravity is going to start slowing you down, times time squared. Now, notice this equation becomes a quadratic equation. So I have a t and a t squared. This is a quadratic equation. So the thing I'm going to do next is set this up in a quadratic form. And when I do that, I can write this as 2.5 meters from both sides, so that I can get everything on one side of the equation. And when I do that out, you should get something that looks like this. 1/2 negative 9.8 meters per second squared times t squared plus 20 meters per second times time minus 2.5 meters equals 0. This is the general form of a quadratic equation, and there's one more step I can take to simplify this equation, and that's to multiply negative 9.8 by 1/2. And when I do that, I get negative 4.9 meters per second squared times time squared, which I'm actually going to write in a different color so we can really see that it is a quadratic equation, plus 20 meters per second times time minus 2.5 meters, and that's going to equal 0. So this is the general form of a quadratic equation. Now this equation is a quadratic equation. If you ever think back to math, you've seen equations of the form ax squared plus bx plus c equals 0. Now in this case, this a term is equivalent to this negative 4.9 meters per second squared. And this b term is equal to this 20 meters per second. And the c term is equal to this negative 2.5 meters And so what we need to do now to find the solution to this equation is use the quadratic equation, which says that, in this case, my variable is time, not x. This is going to be equal to negative b plus or minus the square root of b squared minus 4ac. And in this case, a is not the acceleration due to gravity. A is just the coefficient of the squared term divided by 2 times a. And now when I do this, my b term, in this case, if we look up here, this is my b term. So this is going to be negative 20 meters per second. And maybe I should put that in parentheses. Plus or minus the square root of b squared, which in this case is 20 meters per second, quantity squared, minus 4 times a, which in this case is negative 4.9, negative 4.9. That's going to be a meter per second squared, times c, which in this case is a negative 2.5 meters. And I'm taking the square root of the entire term. And now when I do that, I need to divide by 2 times a. I'm dividing the entire quantity, 2 times a, which is in this case negative 4.9 meters per second squared. Now I'm going to begin to simplify this term out. And when I do that, I'm going to maintain or keep using all of the units so that in the end, you see that you get units of seconds. So in this case, this 200 meters per second squared will work out to be a 400 meter squared per second squared. And I'm going to subtract that from 4 times the negative 4.9 times negative 2.5, which works out to be 49 meters squared per second squared. Notice that this will be a meter times another meter divided by a second squared. And then I'm going to take the square root of that. And again, I'm still going to divide by 2 times negative 4.9, which works out to be negative 9.8 meters per second squared. Now, when I simplify this out further, I'm still going to get negative 20 meters per second plus or minus 400 minus 49, which would be 351 meters squared per second squared, and I still need to take the root of that, divided by negative 9.8 meters per second squared. Now, I can rewrite the top as minus 20 meters per second plus or minus the square root of 351 meters squared per second squared, which will work out to be 18.7 meters per second. And I'm going to divide that by negative 9.8 meters per second squared. And now to simplify this even further, what I'm going to do is I'm going to parse this out. So in this case, this is going to be minus 20 meters per second plus 18.7 meters per second divided by negative 9.8 meters per second, and or negative 20 meters per second minus 18.7 meters per second divided by negative 9.8 meters per second squared. Now when this term is simplified, you get negative 1.3 meters per second divided by negative 9.8 meters per second squared, which works out to be 0.13 seconds. And when you simplify this term, what you get is 38.7 meters per second divided by negative 9.8 meters per second squared, and this simplifies to be 3.9 seconds. Now, you know that the total time that this person is airborne for is about 2 seconds. Now, in this case, this would imply that this person is airborne for a greater period of time than they actually are. So the answer is not going to be 3.9. The answer is going to be 0.13 seconds. Now, there's a good way to check that, and that's by plugging it back into the original kinematic equation. So in this case, we have delta y equals v initial times time plus 1/2 acceleration times time squared. So what I'd like to do is check that given this period of time, I work out to be a distance of about 2.5 meters. And to do that, again, we just plug in the information that we're given. 20 meters per second was our initial velocity, times the time that we just figured out, which was 0.13 seconds, plus 1/2 of the acceleration due to gravity, which in this case is negative 9.8 meters per second squared, times the square of this time, which is 0.13 seconds squared. And when I work that out, the distance that I get is 2.5 let's say 1 meters. But notice that this is the approximate distance that we were assuming that you traveled. So our estimate of time turned out to be correct.